the moment G, of course, is the subset, note right away that W, of course, W defines the topology of the matrices, right? P-adic topology. This is clear. So by its very definition, G is an open neighborhood of 1. So it certainly is an open subset. Now, secondly, I mean, you see from this, I mean, here 1 is, of course, the identity matrix. So this means, right, that the entries of G outside the diagonal are integral, and on the diagonal they are congruent 1 modulo the maximal ideal. So defining inequality implies that, I mean, if I have a G in G, then it's integral, and it's congruent 1 modulo pi to the e. And that means, of course, its determinant, so it follows that the determinant is a unit in OE, and so G is invertible. I mean, I should say G is in GLN OE.
So Peter, you really want, is that an omega then that you're using?
Yes.
Elements of G.
I'm sorry that omega and W is maybe difficult to distinguish. So this is the omega.
And that's W.
And this is W. So G is an open subset of GLN OE. Okay, now let's go through various computations. So omega of G inverse is W of G inverse minus 1 is W of minus G inverse G minus 1. And now we can apply, first we can apply this rule, and then on the other hand we have for minus G inverse, we have this here at 0. So this is bigger or equal to W G minus 1, which is omega of G. So this implies, of course, that with G, also G inverse is in G. I mean, here in the whole okay. Here for G in G. So then we have G inverse is in G. And then, of course, by symmetry, omega of G inverse is omega of G. And also, I mean, using 3 then, right? 3 using 3, you see that G actually is a subgroup. Is a subgroup. GLN, open subgroup. Okay, so then next, I mean for 2 elements now. Omega G minus 1 H is W minus 1. Now this, so just inside the parentheses, I divide this as G minus 1 times h minus 1 plus g minus 1 minus 1 plus h minus 1. And then using these two rules here, I see that this is bigger or equal to the minimum w g inverse minus 1 and w h minus 1, which is now by definition minimum of omega h minus g minus 1, sorry, and omega of h. But we know already that this makes no difference here, so it's the minimum omega g and omega h. Then for the commutator, so again for two elements g, h, and g, omega of the commutator w commutator minus 1. Now this inside the parentheses I re-express as g minus 1 times h minus 1. I mean, here I write the additive commutator, so to speak, of these elements, h minus 1, g minus 1, the whole thing in parentheses, and then I have to multiply by g minus 1, h minus 1. So again, by the same, by this here, and using that these g inverse, h inverse have w0, this is bigger or equal to w of this additive commutator, which then by the first relation is bigger than the minimum of w g minus 1 h minus 1 and w h minus 1 g minus 1, but again both of them are bigger or equal to the sum w g minus 1 plus w h minus 1, which by definition is omega of g plus omega of h. Okay, and finally, so for, let's say, I mean, for one it's somehow by convention true, but anyway. So omega of g to the p so now here I insert artificially g plus 1 minus 1 to the p minus 1, which is w. Now we expand this, sum, say j equal 1 to p, p over j, g minus 1 to the j. And now we pull out the first, so this is the first term is p times g minus 1. And in the rest I also can pull out p and g minus 1. And the rest is then j equal 1 to p minus 1 certain integers, aj times g minus 1 to the j. And you see this second term, here, this sum here, right? I mean, the W of this sum is strictly positive because I have here positive exponent. So W of this here is strictly positive. And this means W of the second summand is strictly bigger than W of the first summand. And so this is equal to W of P times G minus 1. This, of course, is, I mean, multiplying the matrix by P means multiplying the matrix entries by P, so this comes out as 1, right? Plus W G minus 1, which is omega of G plus 1. No, I think it's correct. I pulled one out here.
Even before that.
G minus 1 plus 1. G minus 1 plus 1.
You want to say G minus 1 plus 1.
1 powers of G
Oh,
minus
here, sorry. Yeah, of course. Yeah.
With J is P, you don't have P.
What?
If J is P, you don't have P as a vector. PP is...
If J is, yeah, right. If J is P, I have to use, okay. I have to, that's right. But still, I mean, the argument is correct, right? But I have to write it, I have to write it in a different way, you're right. So, I mean, strictly
You
speaking, I
have got
can...
P minus 1.
Hmm?
You only go up to P minus 1.
No, but I have here the last term. He's right. I mean, if J is here
right.
P, I don't have. So this is P minus 2. And then I have plus G minus 1 to the P. And
that's at least P times omega of G.
this is at least P times omega of G, which of course I don't, which is not sufficient for the argument.
G minus 1 to P minus 1 is greater equal than 1, yeah? Because it's
Why you have to
than
use
1
that?
by P minus
I
1.
mean, probably I have to look.
You have to use that.
I have
omega
to.
G better than 1 over P minus 1.
Oh, no, it's strict. It's. No, you see, this is really P times. Yeah, no. This is okay. I mean, it's P times, so it's strictly bigger than P over P minus 1.
Well, what
Right?
you really need is it's P times omega of G, which is P minus 1 times omega of G, so that's at least
Yes.
1 plus omega of G.
So it's strictly bigger then, but it's strictly bigger because I have this. No, you see this here, W, so W of this here is 1 plus omega of G. Is I mean, yeah, okay, is
Greater.
1 plus omega of G. A W of G minus 1 to the P is bigger or equal to P times omega of G. And I mean, that should be
You
strictly bigger than this one because,
You separate them out as P minus 1 times omega of G and and a single omega of G. Because omega of G is at least 1 over P minus 1, then the P minus 1 times
Yeah.
1 over P minus 1 is at least 1, so this is bigger than
right,
1
it's,
plus
but
1.
it's strictly bigger than 1. Okay, I can do that way, yes, that's right. Okay. So omega is a p-valuation from G. And of course, it defines obviously defining the topology.
Is this the first time that this lower bound on the values appears?
Probably, but I mean, this is an example, right? I mean, I have not. I mean, to get the I have not used any axioms here, right? I mean, this is an example. So in this sense, but of course, I mean, if I want the axiom A, then I somehow have to put it in here, right, in the definition. But probably you are right. Maybe in this calculation we actually have also used it. Yeah, this seems the case that it's that probably we have used it.
If n equal 1 and a p-squared unity, then D would fail.
Yeah.
If you didn't
Yeah.
use the inequality.
Yeah. So I mean, exactly. So if I would relax the definition here, then not only the first axiom would fail, also the last one would fail. That's right. Okay, so this is at least gives one class of one big class, because, right, I mean, I didn't write this down, but it's obvious that a subgroup of a p-valued group is again p-valued. So this gives a lot many examples of
Sorry,
p-valued
did you
groups.
define p-valuation?
Yes? I hope so, last time. Right, last time. And I repeated the axioms. These are the axioms. The group is this function omega from G to 0 infinity. Maybe I should write it not that way. Okay, so now let's go back to the general situation. Let me first repeat here, because I'm going to use this. No, we don't need this anymore, so I can write down here another list of commutator relations, which I need. Well, actually, I think I can do this later. Do I want to do it now? Yeah, maybe I want to do it now.
Actually, also for the last computation, it's not need really that omega is bigger than 1 over b minus 1. You make only that it's different. If you look at the inequality, this is what it is.
I mean, I would have to write this down to see it, so maybe I can do it afterwards. So let me remind you of 3 standard commutator relations in any group. So this is how the commutator behaves with respect to a product in one component, and then the most complicated one is somehow the non-commutative version of the Jacobi identity, and it will turn in this one. I mean, we need it for this purpose. So GH, H, K, H inverse times HK, KG, K inverse times KG, GHG inverse. This triple product is 1. I mean, the rule is, this seems a little bit complicated, but this is a simple rule, right? I mean, these three elements, they are cyclically permuted here. Now this comes in front, and then the next comes in front. And for conjugation, you use always the element before here. So in this way, it's easy to remember. Okay. So now let us, I mean, these, right? I mean, we had defined already these subgroups G nu plus of elements where omega is bigger or equal to nu or bigger, strictly bigger than nu. And so these were normal subgroups, so we can introduce the quotients. Gr nu G is defined to be G nu by G nu plus. And then, right, I mean by C, by the axiom C is a abelian group by C. So I can take the, so we form the graded abelian group G, which is the direct sum over all. I mean, for simplicity, I write all nu bigger than 0. Of course, the first ones don't appear, but anyway, nu of G. So this is the fundamental object for everything. I mean, for a while, for whole while, everything what is going to come somehow crucially depends on the investigation of this object. So, I mean, when we use the usual language, right? I mean, the elements in here are called homogeneous. I will use letters like psi of psi zeta or so for them, of degree nu. And, I mean, such a psi is a certain coset, G nu plus, and then G is called a representative for this element. Now, the point is this has a lot more structure than just being a graded abelian group. So first of all, so let me say this. So G has a lot more structure, and we will spend now some time to uncover this structure somehow. First few things are very easy, and then there is something more difficult, which will need a whole paragraph somehow to set it up. So first of all, right, by D we have that P times any homogeneous element is 0 for any homogeneous, and therefore then of course for any. So this actually means that this is G is an FP vector space. So first observation. Then second observation, let me formulate this as a lemma. So for any two nu and nu prime, the map from gr UG cross gr U prime G to gr U plus U prime G, which maps psi eta to the commutator, which I define. I mean, the moment there's a definition, I use the commutator. So it's the commutator of GH modulo, so it has to be nu plus nu prime plus, where these, of course, are representatives, where G and H are representatives of psi and eta, respectively, is a well-defined bi-additive map. And satisfies, this is obvious, right, that psi comma psi is 0. And this is here 1. Okay, so let's first of all, right, I mean, we have, I mean, if we of course we have to show two things. We have to show, I mean, maybe even three things, but the first one, right, follows from C. So C says that this commutator indeed lies in G nu plus nu prime. So then at least this makes sense. I mean, this coset does lie in here. So this makes sense. But then we still have to show that it's independent of the choice of the representatives and is bi-additive. So, so for this, let's do the following computation, which does both at the same time in some sense. Let's take another element. Let K, which I assume in the moment to lie in G nu prime, I allow it in G nu prime, be any other element. So then, right, I mean, if I do this here, and just let me write it immediately for the cosets, so then I can use this relation B here and get that it's GH H GK H inverse G nu plus nu prime plus. And now you see, I mean, this, of course, H lies somewhere. I mean, it lies in here, but this is far from this here possibly. But G, the commutator G comma K, I mean, K is also in G nu prime, so this commutator also lies in G nu plus nu prime. And therefore, we can apply remark, which one was it? 5.1, right? Which said that always the gr nu G is central in G mod G nu plus. So therefore, in this modulo, this normal subgroup, this thing commutes with any other element. And therefore, the H goes out, and I have GH, GK. Now, if this is even, you see, if k is even in G mu prime plus, then G comma k is in G mu plus mu prime plus. So then you see then the whole, this whole thing, or if you look at here, I mean, it doesn't matter, disappears. And we have GH is the same as GH. Okay. So this means it does not, in the second component, it does not depend on the representative. And then this equation means it's in the second component, it is bi-additive. So use then for the other component, but does it in the same way with A. So use A for the first component. Okay. So by bilinear extension, we obtain a graded FP linear map square brackets from Gr G cross Gr G to Gr G. And satisfying already, obviously, trivially, the antisymmetry relation. So satisfying psi, I mean any, okay, psi 0 or any. Psi G. So now what we need is the Jacobi relation. For any okay, and as you can guess, of course, this is C over there. So let's assume, so we have this theta, psi, eta, let's say degrees nu prime, nu double prime, and representatives G, H, K. And then by C, so, right, I mean, for these three elements, I write down C, except that where I can, I used already the notation for the coset. So I have theta psi, and then I have somehow the conjugate coset H K H inverse G mu double prime plus I should have said this explicitly. I didn't do it, but I mean, right? I mean, I of course in Gr I use additive notation because in abelian group I mean, the product is defined by the product in the group G, but still, in GR, we use additive notation. So, xi eta, and then k, g, k inverse, g mu plus eta, zeta, and g, h, g inverse. H is mu prime plus. So this is 0. And so all we have to I mean, all we have to observe now is that, again, by this remark 5.1, the set of representatives of any given homogeneous element is invariant under conjugation. And so I can everywhere here omit the conjugating elements, and I get my corresponding homogeneous elements. Okay. So altogether, curl G is a graded Lie algebra over Fp. But this is not the end of the story. I mean, the most important ingredient, structural ingredient, is still to come. But so for the last piece of structure, we need preparation. I mean, this is much less trivial. Of course, the idea is clear, right? I mean, we also want to use this here somehow to appear in the structure of this Lie algebra. But this is to see that this is all can be done in a well-defined way is much less trivial than the other things. So I have to insert a section on something I suppose the unabelian people are very familiar with. So we have to study something in this group, and for this we need even more somehow formalism. So I mean, this is all well covered in Bourbaki, for example, so I will only report on it. I will not, I mean, the final technical result I will prove, but the whole machinery I just report on it because this is well covered in the textbooks. So by M, I denote the set of all non-commutative monomials in two variables. X, I call them X and Y. So if you want a formal, I mean, just sequences, I mean, finite products of X and Y in some sequence, where the sequence matters. If you want a formal definition, i.e. the free monoid on this set, on this two-element set, X, Y. Now the usual notations, if I have such a monomial, say mu is the product of mu 1s up to mu d, where each factor is either x or y, then d is the degree of mu. And then I let denote by some kind of Gothic M upper D is the free abelian group on the monomials of degree D. Okay. So now on the other hand, I mean, somehow I don't remember, this is not quite correct how I write this, but I don't remember how it is done. So the M without D is defined to be the Magnus algebra in X and Y, which is simply the ring of, I mean, non-commutative formal power series in X and Y with coefficients, with integral coefficients. Here, in this section, somehow everything is integral. There is no O or anything. It's coefficients in Z. So an element in here, right? I can write as so F is sum C mu over all monomials, and then C mu with the coefficients C mu being integers. And we can, of course, we can view this also. Can view this right as the direct product of these. So M is also the direct product over all degrees of these MDs, where F corresponds to F upper D, and FD is the part where, right, I mean FD with F upper D is the sum of over all mu of degree D. C mu. And then, moreover, I also need odd of F. This is the smallest degree minimum over all degrees of the mu's which really occur, so that the coefficient is non-zero. So this is the order. It's the order of f. Infinity if it's zero, f is zero. And also it's convenient, let me, I think, to introduce the following somehow notations. If the order, if I have two such power series and their difference has order at least L, then write f is congruent f prime mod degree L. And moreover, so if all monomials in the difference of degree less than L occur with coefficient divisible by p, then write f is congruent f prime mod p comma take L. It's just shorter notation for these things. Okay. Actually, maybe I can write down here. No. Another exercise. So let A be an integer, f in M, and u in M of degree at least, actually, not sorry, of order at least 1. So the first statement is that it's very easy to see which f's are invertible in this ring. And this is the case if and only if the leading, the constant coefficient is plus or minus 1. And this is very easy to see by using the geometric series. So in particular, note, we will use this immediately, is that 1 plus x and 1 plus y, they are in units in this ring. And then we need the following congruences later. So if I have such a unit, say here is plus 1, and I raise it to some power a, integral power a, then this is congruent 1 plus a u, the part of the order, the leading part, so to speak, modulo the next higher degree, modulo degree odd u plus 1. And thirdly, if I raise this to a power which is divisible by p, then this is congruent 1 plus u to the p a is congruent 1 modulo p and degree p times order of u. So now let's denote by f. I mean the object in the title. Actually no, let me do it the other way. So let f in the unit group of M be the subgroup generated by 1 plus x and 1 plus y. And so then one has the first fact is that this f is actually free, is the free group on 1 plus x and 1 plus y. So I will give you here, as I said, this is just reporting, so but I will give precise reference. So this is Bourbaki, Lie groups and Lie algebras, chapter 2, paragraph. Okay. So then next, next define Fn. This is all f in f. Right, I mean, of course, by definition, the power series in f all start with 1. So, I mean, now we take those which have a 1, but then they start much later. So the odd of f minus 1 is at least n. And then, actually, these things also have numbers. I may need that. So this is 6, 2. This was 6, 1. Which says that this is the central series. So first of all, f1 is f. This is clear, as I said. In f, everything starts with a 1. But then, I mean, the assertion is that fn plus 1 is commutators fn with f. And this is Bourbaki, chapter 2, paragraph 5.4, theorem 2. So as a corollary, I have that all these quotients here is a free abelian group. Actually, is a finally generated free abelian group. And the first step, of course, f1 by f2 is the free abelian group on two elements. But I won't give a reference here because we look at this. We will look at this much more closely. Observe. I mean, now we repeat something here in this context, which we just have done at the end of the previous paragraph. Namely, observe the abelian group f, which is the sum of the natural numbers fn modulo fn plus 1 is a graded Lie algebra over the integers with the Lie bracket given by, right, the same way we did it before. So for FL modulo FL plus 1 cos Fn, say Fn plus 1 to F L plus n, Fl plus n plus 1. So this is by exactly the same arguments. I mean, we did not, for this, we haven't really used much, right? We have used in some, in particular for the G, we did not use this here at all. We used this, this remark that the step, such a filtration step is central in the whole thing, but this is now, of course, the analog of this is the central series. So this is certainly also true in this context.
I'm
So
sorry, about the corollary, it's hidden right now, but I mean, I guess I know it's true, but why is the freeness of immediate?
No. I said it's not obvious, and I don't give a reference because I will give with a reference a much more precise statement, which will in particular show that it's free finally generated. Okay, so this is one thing. Then the other thing is there's a Lie algebra in a. Of course, we have a associative algebra, the M. So any associative algebra is also a Lie algebra. So M is a Lie algebra in the usual way. For the additive Lie bracket. Minus Fe, and so define L in M to be the Lie algebra generated by X and Y. Lie subalgebra generated by X and Y. So then we know the following things. This L, I mean, this is not particularly surprising. L is the free Lie algebra on these two elements. And is naturally graded by L, in fact, is the direct sum of its intersections with these pieces of the Magnus algebra. Moreover, furthermore, each of these pieces here, L intersected MD, is a direct factor, as an abelian group, of course, of MD. So this is, so in particular, this is also a finely generated free abelian group. Now all this is proved with this, there is this theory of the Hall basis, and so this is a bit
Direct
technical.
factor means as abelian.
As a abelian group, yes. As perhaps you are right, I should write this. As abelian group. Okay, and then there's the following theorem. With which I finish for today. The unique homomorphism of graded Lie set algebras from, say, phi from L. I need this notation later, I think. That's why I need to give this a name. To gr F, sending, right? I mean, this is free. The left is free, so I can get by its, of course, what does free mean? It means it has the obvious universal property, so I can send x and y somewhere, and I get a Lie algebra homomorphism. And if I send them to homogeneous elements of the corresponding degree, then it will be a graded homomorphism. Is an isomorphism. And that, of course, is not a very explicit description. It's a description by universality, but the point is the inverse is very easy to describe. Its inverse is given by sending, take a coset, take any representative, F, and send it to its homogeneous part, Fn. So this is totally explicit. Okay, next time then we use this to prove a technical statement about certain commutators in the free group, and that's what we will then apply to get the additional structure on group G. That's it for today.